Hey, what's up, guys? This is Chung. So today, let's talk about a special topic, which is the mini queue implementation. Mm, some of you may know that, right? So a mini queue, at least in Python, it's I mean, the mini queue as in itself, it's actually a list, but the implementation on top of that, it's actually a binary tree. So that so for the mini for the mini priority queue, right? And there are like um, push and pop operations, and each push and pop operations, the time complexity is log n. So how does it achieve that time complexity, right? By by doing the push and pop. So to answer that question, let's try to visualize some of the priority queue, right? So that's going to be a so since the priority queue the itself is just nothing else but a list. So to implement this, to use a idea to implement this one, we have to somehow find a way to represent the parent and child relations. Okay, right? So let's say we have this kind of list. So the way the priority queue or the mini queue implementation works is that, so here's the parent and child relations. So we have 0, 1, 2, 3, 4, 5, 6, 7. And at each of the I here, right, its child, it's actually 2 times I plus 1. This is the left. The left child is this. And the right child is this. 2 times I plus 2. Basically, so the left one, so the first element of this array is always the root, and for the root, the child is this. It's this one. That's the left child, and this is the right child. And for this node, right, the uh, the left child is which one is this one? So it's this one, and then the right child is this one. So similarly, for this one, the left child is 2 times is this one, right? And the right child is this, and so on and so forth. This one is like this, and this one. It's 8. That's how we define the parent and child relations, so that given like an index or given a parent, we can easily calculate the it's either its parent index or the child index. And why is that? Like I said, since the implementation for the mini queue is like a complete tree. So what is a complete tree? Complete tree is uh, every node has two has has two child except for the last level. It means that let's say we have this tree here, right? And this one. So something like this. So this is a complete tree. I'm sorry, yeah, I think it's a complete tree. Basically, all the levels they all have the they'll have the full nodes except for the last one. And if we try to populate this tree one by one, basically from top down and then from left to right, then you find out actually this formula align with the index on this tree. So let's say we add the first one we add is 0, right? The second one we add is 1 on the left one. Third one is 2, and then we keep adding from left to right. So 3, 4, 5, 6, 7, and 8. So so parent 0, the left child has 1, right child has 2, and the parent this node 1, his its left child is 3 and 4, which is the same as this formula. Same thing for all the nodes. So for 2 is 5 and 6, for 3 is 7 and 8. That's why we choose to use this formula to represent the relations between the parent and child. Okay, so now we have the relations. And what's next? So another uh, characteristic or property for a mini Q binary tree is that every every parent node is smaller than the child node. So that means that which means that the higher level the tree is, the smaller number it is. You will get. That's why the root node is always the smallest number among all the nodes in this tree here. And so our purpose for the push and pop is just to maintain this structure in this binary tree. Okay, so to maintain that, since we have push and pop, so let's talk about them separately, right? And so let's see how will this algorithm handle the push and pop. So for example, let's say we already have like a tree, right? Let's say we have 4, 5, 7, right? And then 6, 8, and 9. So right now, this is like a valid a mini Q tree because all the nodes on all the parent nodes is smaller than the child node. And so how this push work is that every time we always add to the end of this tree, which means that to the last one of this tree. So basically, let's say we're adding like a push 2 here, right? So we're gonna add this to here. And the reason we always add it to the end is because since the data structure we use is like a list or array, right? If we push it in right into the middle, so every elements after that needs to be shift. That's gonna be a kind of slow. That's why. But if you always append to to the last one, then it's all one time. That's why that's why we always push to the last element of the tree, which is like this way, like this position, right? And after adding the element to the last of the array here, we'll try to basically move this array up based on the value here. Since this one currently is 2, and 2 is greater than 7, which it breaks the our property. So which means that we need to swap the 2 and 7 to keep the characteristic of this binary tree. And so that's why we're gonna swap this 7 and 2. So now we have 7, here we have 2. And we keep doing this until we have reached to the end. So then we check if the 2 is smaller than his parent. Yes, right? So we're gonna swap this 4 and 2. Right? And until it's either reach to the top one or the parent is not great, it's not smaller than the current one. Then we stop swap the the moving, right? So it's actually you can think it's very similar like what like the a bubble sorting, right? Basically, we're trying to bubble the smaller number up until there's no need to keep bubbling up. And as you guys can see here, right? Since this is like a complete tree, to bubble this number up, so the worst case scenario is that we need log n time to do the bubbling because we only need to at most do the height of the tree's number of swaps. Yeah, so that's gonna be the push. The push is a little bit easy, right? And now the pop. Hmm. So the pop. Okay, so and let's use the same example here. Let me try to remove this. Hmm. So let's say we have two, right? So that's gonna be 2, 5, and this is 4, right? 4, 6, 8. Let's say 7, 9. 7, 9. So how does the pop works? So obviously pop is we need to pop this element out. But after popping this element out, first we need another root, and second, we also need to maintain the structure or the property of this binary tree. And again, right? Again, so when we remove the element from the array here, we don't want to move it right in the middle because, like I said, if we try to remove it in the middle, that means that we will basically shift the rest. That will be kind of slow. So again, just like how we do the push here, we're try. So first we'll try to swap. We'll try to move this element to the end of the array here, so that we can just pop it within O1 time, and then we'll try to like do another like heapify, right? We're trying to move this element down because we're to maintain the conditions. So here's what I mean that. So first, let's see, we try to remove 2 here. So the first thing we want to do is that we're gonna swap 2 and 9. So now we have 9 here, and then we have 2. Since the 2 is the last element, we can simply do a pop, right? So now the pop, this 3, the 2 is gone. So what's left is 9. It's a tree with a 9 as a root. Then we need to do a heapify down. I call the push heapify up, basically move this thing up. So for after popping this element out, I need to do a heapify down, which means that I have to check if this current root is the smallest number or not. Obviously it's not, right? But it could be, right? And so we need to somehow move this down. So how do we move it down? So the heapify down is a little bit complicated than the moving up because we need to compare the left and right child. For example, so the left child is 5 and the right child is 4. So we definitely need to move this down, but in which direction? Either to the left or to the right. Okay, so remember, right? We always want to make the root to the smallest number, so which means that we need to compare the left child and the right child. And we need to move to the direction which has a smaller number. In this case, is 4, which means that so currently we have 9 and 4. Since 4 is smaller than 5, we'll need to swap this 4 with 9, right? So now the top one is 4. The root is 4. Now here we have 9, and then we continue our comparison. So is 9 smaller, is greater than 7? Yes, it is. Since there's no right child here, that's why we're gonna keep heapifying down. So we're gonna swap 7 and 9 here. Yeah. So now we have like an updated binary tree, which also like have the root for the current smallest number. And similarly, right? So to heapify down, it's also log n time. And basically that's how we maintain the structure of this binary tree. Cool. And yeah, I think we can start the implementation now. Mm, yeah, I'll just use this like notepad, the play zone to do the implementation. So let's see, we have priority queue, right? So that's the first one, and then we have heap push, right? And we push like an item, and then we do a heap pop, right? And another item. So the reason I use item, not an integer, is because we could, so the priority queue, there could be any element. It doesn't have to be a number. It could also be like a tuple, right? Or a pair. So that's why I use item here. Mm, so for the push, so the push is kind of easier because all we need to do is we just need to first we append the current item to the end of the list, and then we will basically do a heapify up, right? And then we'll pass the index. So for the index, since it's the last one, right? So we just need to get the nums of priority queue -1. That's the last index of that. And okay, so let's implement that one first. So for a heapify up, right? So the key is the index, and so first we check if the I is greater than 0, because if the I is 0, it means that it's a root. There's no need to keep heapifying up. And then for current one, since we're going to compare with the current index parent, we need to get the parents first, right? So for the parents index is going to be I minus 1 divided by 2, right? So why is that? I think this is also a kind of, it's pretty straightforward, right? So let's say we have this one. So we have 0, 1, 2, 3, 4, and 5. So for 1, the child is what? The child is 3 and 4, right? So but given 3 or 4, we need to get 1. So how do we get that? So first we do a 3, we do this index -1, then we divide it by 2. So 3 minus 1 is 2, 2 divided by 2 is 1, right? Same for 4. 4 subtract 1 is 3, 3 divided by 2 is also 1, sorry. So this is 1, yeah. All right. So for the parent, right, and then we compare. So if the priority QI is smaller, right, than the priority queue of the parent, then we swap those two things. So priority QI dot priority queue parent equals the priority queue parent dot priority queue I, right? And then since we need to recursively doing these things, we just do a heapify up of the parent. Yep. So we just keep doing that until there's no further heapify. I think I did there's a typo here. Heapify. Yep. So that's basically the heapify up. Now for the heap pop, right? So for the heap pop, like I said, we need to do a answer, right? So we're gonna store the answer to the priority queue 0, and then we're gonna swap the 0 one with the last one. Priority queue -1 dot priority queue -1 priority queue 0. Okay, and then we need to pop the last one. And then we'll do a heapify down from 0, and then in the end we return the answer. Yeah, so that's that. And so to heapify down, right? Similarly, like the heapify up, but since we need to compare the left and right child, so the implementation is a little bit more complicated. So first we have left equals to 2 times I plus 1, right? And the right equals to 2 times I plus 2. And also since there could be no left or no child or no right child, and so there are like different implementations. So for me, I just define like a smaller child index, right, equals to -1. That's the start, and a smaller child value equals to none. And then if the L is smaller than the length of the priority queue, so the reason we are comparing this one is because if the current if the current node doesn't have a left or right child, and then the left or right index will be greater than the current length. So that's why we do a check here. So if that's the case, right, and we'll just do a smaller child value index equals to the left, and then smaller child value equals to the priority queue left. Now for the right one, if the L, if we also have like a right child, and then we do this, right? So if not smaller child value, or the priority queue dot right is smaller than the smaller child value. So here I'm saying that if this one is none, which means that if there's no left child, or if there is a left child and the current one is smaller than the left child, then I'm going to update. Yeah, I'm going to update this one here, these two values with the right child. Now, in the end, we simply do this, right? So if the smaller value is not empty, right, and the priority queue I is greater than this smaller value, then we just need to do the keep recursively calling the heapify down. But first we need to swap, right? This one priority queue this one dot priority queue I, right? Because like I said before, before the recursive call, we have to move this great a bigger value down to one of its child, and then we just recursively calling the heapify down with the child index. Yep, I think that's pretty much it is. Yeah, so let's try to do the testing, right? So let's say we do a heap push, and we have two. I'll just make a few copies here, right? So we push, push, push. Let's say we have 1, 3, maybe 0, 0, 8, 3, 9, and maybe another 14. So let's do a print. Do a print priority queue. Let's see what we get here. Yep. So you can see here, right? So the smallest number is always always the always at the first item, first index, right? But the rest is not sorted because because we only guarantee that, so the parent is smaller than the child. So we're not sorting the rest. And yeah, so how about the pop? So let's do a pop and heap pop priority queue, right? So, and then we print this one again. Okay. So if I run this one here, yeah. So So after a few pops, so every time we pop one element out, so after the first pop, right? I mean, zero is out, and then the one, it will be the one becomes the current smallest number, and after one is out, two will be the current smallest number, and then three, another three, 8, 9, and 14. In the end, there's like not nothing to pop out. We have like this. Oh, I think this is because the here. And if we try to pop an empty list in Python, it will throw an exception. So what we can do here, we can do this. So if the particle is not empty, then we just do this. Else, uh, else we can just return like -1, something like that, right? So if I run the code again, yeah. So now we don't have any errors because we have already handled that here. Mm, yeah, I think it works, right? We're not printing the elements got popped out. We're always printing the remaining priority queue. So after a few like pops, there's nothing in the priority queue. Cool. I think that's pretty much it is, right? I mean mm, yeah. So just to recap, right? So the priority queue, we so the priority queue itself actually is nothing more than a list. But we're using like this the a tree structure concept to manipulate the elements in this priority queue. And the way we're doing this, we are like defining like a child and parent and child relations by using this kind of formula. And then the next important property is that all the we're trying to maintain uh, for each node, uh, the node itself needs to be smaller than any of its child. That's why we're doing this kind of heapify up and heapify down for the heap push and heap pop. And cool, I think I'll just stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.